Study the evolution of the universe. It's a hard science. We have facts. It's not astrology, it's not guessing, it's not subjective. We make definite measurements. But it's on a very large scale. We're measuring things that are many, many, many millions of light years. So we're not really into the details. We couldn't tell you how a star actually formed, and heaven knows we couldn't tell you how a human formed. But we could tell you how maybe the universe formed from just very humbling beginnings. Right now we are within 1 kilometer of the geographical South Pole. And we're here to study the cosmic microwave background. We bring our telescopes to look through the incredible transparent skies that are available here to look at the very early universe, when it was roughly 1 part in 35,000 of its present age. The cosmic microwave background is this faint glow coming from the origin of the universe. The very early universe was a hot, dense, ionized plasma that glowed as photons of light interacted with charged particles of matter. But as the universe expanded and cooled, eventually the light didn't have enough energy to keep the charged particles separated. Essentially, atoms could form. When that happened, the light no longer interacted with the matter and just traveled in straight lines. We should be able to see that early light today, 14 billion years later. But in the process of those 14 billion years, the universe has been expanding and the wavelengths of light have been stretching. So instead of looking for visible light, we're detecting much, much longer wavelengths of light, which we call microwaves, and which we can only see using specialized instruments. The instrument which we've actually made measurements with now, and we've done very well with this, is called DAISY, the Degree Angular Scale Interferometer. An interferometer is a weird type of telescope in that it actually is comprised of a lot of smaller telescopes. You might have seen pictures of the Very Large Array in New Mexico, big 25-meter telescope stretched over many kilometers. This is the same idea here, except for imaging the cosmic microwave background. We don't want real fine resolution. We want to look at a large region of the sky. And so we have little 20-centimeter diameter telescopes. Each one of these is a telescope. And then we have 13 of them. They work in unison. And what's important for an interferometer is the number of pairs of telescopes. So with 13 telescopes, we actually get 78 pairs. Each pair measures one part of an image. You put it all together, and we get a complete image of the cosmic microwave background using an instrument like this. Well, you might wonder what happens to all the data that DAISY collects. It's quite a bit of data. It's several hundred megabytes a day after compressing it at the South Pole. And then it's sent via satellite and beamed back down to the U.S. and collected here and stored on our computers at Chicago.
I think if you have a large number of point sources contributing to your signal, then you would expect equally ND from them.
At this point, the same team that actually deployed the telescope is now back in Chicago, and we start working on the data to be able to make images, to see what it's telling us. 92 days of data went into these fields, and now we have 140 days of just these guys. So just making those maps is going to be beautiful. We're just looking for small differences in that image. Slightly hotter, slightly cooler of parts. When we make an image of the cosmic microwave background, these hot and cold spots are telling us something about the conditions of the very early universe. For the most part, these hotter parts, a little hotter, are where structures tried to form, where you have matter and things are forming together, and as they come in together, it gets a little denser, it gets a little hotter, and so we can see that. cooler spots, there's places where the matter is actually being pulled away into the hotter spots. So we're seeing the very, very early seeds of all the structure formed in the universe. So the early universe is quite simple, right? You have just these photons interacting with matter. When things get cool enough, finally the photons are free to travel, and matter's free to form structure. But surprisingly, it's not so simple. It involves components which we know very little or next to nothing about. In the early universe, we can look for how gravity on one hand is pulling things together, and the photons are pushing things apart again. And we can solve for that interplay. And what we find is that there seems to be more matter pulling things together than matter that's being pushed apart by the light. In other words, most of the matter appears not to interact with the light, contrary to what we know about all the matter around us. So there is another form of matter we call dark matter, which doesn't interact with light. But what's even more surprising is if you add up all of that matter, we're still missing something. The cosmic microwave background observations tell us we're missing something, and that what we're missing is about 2/3 of the equivalent density of the universe. And that is apparently what's causing the universe now to accelerate. That is, the expansion of the universe is actually accelerating. And we don't know what that is. It's new physics. So what's exciting to me about cosmic microwave background studies, about my own research, is that I'm able to work with a small team of people. It's just a wonderful team of people. And we can make measurements. We can take snapshots of the very early universe. We can learn about the universe as a whole, very fundamental things. And in the process, we're uncovering new physics, which just, the chance for discovery of that is rare. And here we are in the midst of it. It's just a terribly exciting time.